Okay, so as discussed in the previous video, in this one we're going to be talking about directional limits. So as it suggests by the name, it's a limit, a special kind of limit, right, that talks about the direction. But it's not too different from the limits that we've evaluated, right? So, well, in the terminology that we're going to refer to, right, in this video, limit as x approaches 4 from the positive side, and another one would be x approaches 4 from the negative side. So basically what this is saying is, if I have a function x, right, and I have the function has to be the same in both cases because it's the same example, right? So if I have a function x over here, and I'll try to plot it, yeah, that's y equals x, this is 4. So basically what it's saying is the limit as x approaches 4 from the positive end. So what it's saying is the limit is being approached from the right hand side, the right side of 4 basically, and this particular limit is saying that you're approaching it from the left hand side. So essentially the concept is that we need to be able to evaluate the individual directional limits of any particular limit, right? So a limit has to be broken down. If I were to make a tree over here that talks about precisely that, a limit has to be broken down into its positive and left, basically positive right and negative left handed limit, right? So let's do a particular example that tries to illustrate this concept. Well, this example over here, as you all would be able to do by this point, is that when the limit, as we're trying to approach 4 from the right hand side, tries to approach 4, we end up with a 4 because it's a y equals x function, right? So all we're doing over here is plugging 4 or the positive side of that. So we try to do the same for that, but we can see that it's trying to approach 4 from the left hand side, but it's still ending up at the same value of y, right? This turns out to be 4 as well, right? Now let's try to do another example. In this example, we're going to be talking about the square root function. And I'm going to ask you guys to try to evaluate the limit of the square root function. Before that, it's a good idea to plot it so we know exactly what's going on, right? As it turns out, the square root function kind of looks like this. So how was I able to plot this? Well, basically I just took values and I tried to plot this function at those particular values of x. So if my x is 0, the square root function gives me 0. For 1 it gives me 1, 2 something close to 1.41, but I'm going to try to use perfect squares over here, so my problem is simplified, right? 9 is going to give me 3, and 16 is going to give me 4, and so on and so forth, right? So what's happening is that I'm getting this at all these different values. So if that were 0, this turns out to be 1, that's 4, 9, and 16, and so on and so forth, right? So that's how I was able to plot this. What you might have noticed over here is that we're not considering the negative side of this particular function because the square root of a negative number does not exist, or basically it's imaginary, but let's not get into that right now. So if you try to do that, let's break this limit down into two parts as we discussed above. Let's try to approach 0 from the right hand side. If you try to do that, we observe getting closer and closer to 0, but not just that, we observe that we're getting closer and closer to the origin, which basically means one thing: we're ending up with a value of 0 over here, because as x approaches 0 from the right hand side or the positive side, we end up with a 0. Let's try to find the left-handed limit. If we try to approach 0 from the left hand side, what do you think is going to happen? Well, we're going to get closer and closer to 0, but never equal to it. Which means what? Which means that we're going to get a very, very small number that could be 0.00001, but there will be a negative sign attached to it. So what does that mean? It means that the square root of a negative number does not exist, right? Which means what? That the left-handed limit does not exist. Now there's a problem over here. We're getting the left-handed limit in this particular case as 0, and the right-handed limit as the right-handed as 0 and the left-handed as does not exist. So there's a certain rule involved here that we're going to be talking about now. The rule suggests that if the directional limits of a particular limit exist, only then does the regular limit exist. And we know what a regular limit is, right? We know that because in this particular case the regular limit would be x approaching 0 for square root of x, and we broke that down into two parts. We talked about the right-handed limit for square root of x, and we talked about the left-handed limit, right? So the idea is that if this is turning out as a number but this isn't, or in this particular case this is turning out to be a number 0 but that is not, right? This would basically mean that the regular limit does not exist. Does not exist. Which means something else. Which means that if the left-handed limit is not equal to the right-handed limit, the same result would apply. Then the regular limit would simply not exist. So in order, what that basically means, in other words, if the regular limit has to exist, then the left-handed limit and the right-handed limit are supposed to exist as well. And at the same time, they're supposed to be equal to each other, because if they're not, then it's a contradiction. Let's do another example that illustrates precisely that. By this point, you must be very familiar with step functions, right? Let's just write down a step function over here. So this function f of x is broken down into two parts. It gives me the function x when x is greater than or equal to 0, and the function x squared when x is negative, basically, right? Let's try plotting this. So if you were to plot step functions, it shouldn't be that much of an arduous task, but still you'd have to simply divide your task into two parts, right? So first we're going to consider this part. So for x is greater than or equal to 0, actually let's first consider the negative part, because we're going to move from the left to the right, right? Right, so let's do that. It's basically saying that for all negative values of x, I have the function f of x equals x squared. So what's that saying is, अगर मेरे पास -1 है, that's giving me -1 squared 1. अगर मेरे पास -4 है, that's giving me 16. So we all know what an x squared function looks like, right? It's a bell-shaped curve. So what we're going to do is we're going to take the left part of this, because this is working out for negative values, right? So that's y equals x squared for the left hand side, for x is less than 0. What does it say for x is greater than or equal to 0? Well, simply it says that it's the y equals x line. So at this particular point, we're going to draw a y equals x line. So as you can see, it's kind of a weird graph, but it's still a piecewise function, or in other words, a step function. We should not refer to this as a step function. A step function is usually something that looks like this. For a particular domain, like moving from -5 to 0, we have this particular value, right? And at this particular value, 0, we're simply jumping to another value. So that's my function over here. So at this point, there's going to be a hole because this value basically jumps over here. That's known as a step function. This is more of a piecewise function that we're going to talk about, because this example is more relevant here. Let's try to find the limit as x approaches 0 for f of x. So we'd have to break this down into two parts. Let's talk about the left-handed limit first. As x approaches 0 from the left-hand side, we're going to have to use the first function, right? X squared. So the function turns out to be x squared, and what are we going to do for that? We're simply going to plug in a 0, because we know that if it's approaching 0 from the left-hand side, it's eventually going to get closer and closer to 0, but never actually equal to 0, right? Turns out to give me 0. Let's do that for the right-handed limit. So x trying to approach from the right-hand side would give me the function f of x equals x. Why? Because it's getting closer and closer to 0, right? And it's approaching it from the right-hand side. And that's the policy I have here. So as it turns out, it's y equals x, right? It's giving me 0, 0 as well. So the left-handed limit and the right-handed limit exist and are equal to each other, which means what? That the limit at x equals 0 exists. And it's equal to what? Well, we know that it's equal to 0 because that's what the answer turned out to be in the previous part, right? This is something that you guys need to consider. Break down the regular limit into two parts and solve it step by step so that you may understand or may come to the conclusion that the regular limit exists or does not. See you guys in the next video.